Okay, I want to introduce improper integrals here. And the best way to do that is to start with an example. So let's consider the function y equals 1 over x squared. Kind of random, but you'll see why. This is an interesting choice of a function. What does it look like? Well, if we graph it, right, it's, I don't know, it's something like as x gets large, well, it goes to the point 1 comma 1. And as x gets large, 1 over x squared gets small. So it's actually got a horizontal asymptote. It gets closer and closer to the x-axis, right? And actually, as x gets closer and closer to 0, you get 1 over a small number. So that grows, that gets big. So this does something like this. The graph looks something like that, right? Y equals 1 over x squared. And I want to think about the area under this graph, but I want to think about it starting at 1 and then moving to the right. And actually, there's this idea of trying to look at the area of kind of going on forever. So the area from 1 to infinity. I'm going to put a big, question mark exclamation point there just to be like, oh, what? How is that possible? Well, how can we start to think about that? Like the area, it should just be infinite, right? I mean, if it goes on forever, how could you ever have a finite area? Well, let's think about it. Let's compute the integral from 1 to b of 1 over x squared dx. So that's a letter B, not a 6. For various b greater than 1. B was a bad choice, maybe. So for example, if we just did the integral from 1 to 100 of 1 over x squared, that's the same thing as the integral of x to the minus 2. And that's again from 1 to 100. That kind of looks like an infinity sign. So that's negative x to the minus 1, right? Remember, which is negative 1 over x from 1 to 100, which is negative 1 over 100 minus negative 1 over 1. So that's actually 1 minus 1 over 100, which is 99 over 100. So if we integrate all the way to 100, we actually we have area less than 1, but that's going to clearly grow, right? So what if we do the integral from 1 to like a million of 1 over x squared dx? Well, just using some of the steps above, we know that the antiderivative is going to be negative 1 over x from 1 to a million. And, maybe you should be pausing and getting ahead of me on this stuff, because what do you get here? You get negative 1 over a million minus negative 1 over 1, which again, you get a plus 1, you get 1 minus 1 over a million, which I guess is 999,999 over a million. But think about this, this is, this number here is less than 1, but close to 1. This number, think about it, it's really the area, imagine, this, let's just say this, I should have labeled this point as 1 right there on the map, on the graph up here, but just, the area from 1 to 100 is up to maybe, it's off the page, but it's there. But then the area from 1 to a million goes on, way down, way down the page. It's over in, I don't know, New Hampshire or something, depending on which way you're facing. And we still got a number very close to 1, but less than 1. So somehow even going from 100 to a million didn't get us enough area to get over 1, right? And if we just do this in general, you start to see what happens, right? Like the integral from 1 to b of 1 over x squared dx minus 1 over x from 1 to b, which is minus 1 over b minus 1 over 1, which is 1 minus 1 over b. It's actually almost better to leave it in this form. You know, up here I was combining this into that and combining this into that. But really, this is the part this is probably the better form to keep it in, because you realize how close you are to 1, but you're never going to get there. That's the thing that's crazy, right? This is less than 1, no matter how big you make b. And so that's kind of astonishing, actually. It's this idea that somehow we could keep going. Like I said, the area from 1 to infinity, we could keep going forever to the right. We could keep go on forever. And the area is always going to be finite, no matter how far we go. And in fact, so what we do is we say, we define, yeah, I mean, I should actually say that, I should actually write that down, that this number is the area. Area sort of goes on forever. I mean, I guess we haven't really had it gone on forever yet, because we haven't let b go to infinity. That's the point of what we're going to do next. But let me just put it this way. I'll put in quotes, forever, but remains finite, which should be really weird to you. It's very counterintuitive. So the way what we do is we actually define the integral from 1 to infinity, 1 over x squared dx. We define that, it's supposed to be an infinity symbol right there. We define that by saying it's the limit as b goes to infinity of the integral from 1 to b of 1 over x squared dx. Right, so we're just going to think about moving that right endpoint. This b represents the right-hand endpoint of the interval up here at the top, right? I could label some point here like b, and we're just going to slide that to the right. You know, keep sliding that to the right as far as we want, and we've already figured out what this equals. This expression right here equals 1 minus 1 over b. So that's just equal to the limit as b goes to infinity of 1 minus 1 over b. And now if we let that b get larger and larger in the bottom, right, as this gets bigger and bigger, 1 over b gets smaller and smaller. So the limit is actually just 1 minus 0, which is 1. And so we actually say that the area under the graph is finite, even though, kind of like I said, it goes on forever. And it's almost like I could take away the quotation marks here and say, really, we're going to go on forever. We're going to actually go to infinity, and we're never going to get an infinite area. It's just going to be this finite area. And so this kind of integral, so first off, again, it's surprising that we can get a finite answer. We have to develop some intuition here. We won't always get a finite answer. I mean, you will certainly look at some situations where you definitely will not get a finite answer. Surprising that this area is finite. And such an integral, something like this, is called an improper integral, because we're doing something kind of improper, which is we don't really have a right-hand endpoint. It's really improper it's always at one of the boundaries. It's, well, not actually always at one of the boundaries, but it's usually, it's not about the function being improper. It's the bounds of the integral are what are considered improper. We'll see what happens. We'll see it's possible to have finite bounds be improper too, but certainly infinite is this situation that's called improper because you don't, it's almost like not having a right hand bound. So, so this is sort of, we would say something like this is improper, or I guess I should say, this is improper at infinity is what people will say. Because you're not supposed to be able to go to infinity. Okay, so that's the first example. I'll continue with more examples, and then we'll talk about different types of improper integrals. But this was just a quick introduction to the topic. So I am going to stop there.